Scott Gleason, who attended the University of Buffalo, Stanford, and the University of Surrey in England. His PhD was on the subject of remote sensing with GPS signals from spacecraft. He has worked in the fields of spacecraft engineering and remote sensing for over 20 years, including at NASA Goddard, Orbital Sciences, Surrey Satellite Technology, and Concordia University. He's currently a principal scientist at the Southwest Research Institute here in Boulder, and an instrument scientist on the NASA CYGNSS mission scheduled for launch in 2016. Please join me in welcoming.
All right, thank you for the introduction. As I said, I'm from Southwest Research Institute here in Boulder. The main Southwest Research campus is in Texas, but they do have a little group here in Boulder. And thank you for the UNAPCO for the invitation to give this talk. So let me just start this up here. Okay, so I don't really mind. I'll go along in the presentation. If you have questions on a given slide, just raise your hand, jump in. I don't care. You don't have to wait for the end. I kind of tried to time it so there would be some time at the end for questions, but I don't mind questions right when I'm giving the presentation either. Just to give a general overview, as there's an update, and I didn't know how much GNSS people knew. I know some people in the audience know quite a bit, others maybe nothing, so I kind of try to strike a balance as to the background I was going to go over. I primarily do spacecraft GNSS, so it's a little bit of a different animal than some people might be used to. But I did slip in a little section on overview of some on-orbit GNSS missions. It's not like my old presentations where we just talked about some little experiments, but it's really starting to grow, and there's actually another satellite up there now getting measurements quite often. And then I'm going to talk just to get a little bit of background on GNSS remote sensing, the delay Doppler map, and the surface resolution from space that we do get. And then a quick overview of some applications, ocean wind and wave sensing, land sensing, and ice sensing. I left off some applications, so I'm not going to talk about altimetry just for time reasons, but that's other applications as well. And then give a little overview of the Cygnus mission, which stands for Cyclone GNSS. So it's a mission basically that's going to launch next year to study cyclones, wind speeds, and ocean waves and cyclones. And what struck my interest why I kind of contacted UNAPCO was I got wind of the COCONET project. And since there's both Cygnus and COCONET are both sort of studying the same region, more or less, Cygnus is tasked with looking at hurricanes, and its coverage is designed to concentrate on the Caribbean. So I thought there might have been some interesting overlaps there with what Cygnus will be looking at and what COCONET is doing, and possibly some interesting areas for how they could work together in the future. So just generally, I'm going to go over some operational spacecraft GNSS instruments, past and present. The past instrument, and this is the UK DMC experiment. Back when I worked at Surrey Satellite Technology in the UK, I did my PhD there. The basis of my PhD was this little experiment that we put on board an imaging satellite. And we basically just tacked on a GNSS reflections experiment onto an existing imaging satellite. You can see there's a little reflection antenna there and right next to the imager. And it was really just a makeshift last-minute thing where we were just hacking raw IF data off the GPS receiver into a down-looking antenna and processing it all on the ground. And for various reasons, there was only about 25, 30, 40 collections made with this instrument. But it was enough to get my PhD done and kind of validate two key things. One of them, that the signals are detectable in space, and that we can link the signals in space to ocean winds. What came out from this is basically that Surrey, after I left, basically took my work and then improved on it, and then redesigned the algorithm, and then designed an instrument, a complete instrument that could process in real time. And they launched this demonstration on a mission called TechDemoSet, which was launched last year. And this is basically a real-time instrument. TechDemoSet has got the National Oceanography Center in Southampton is the prime science lead on this, and Surrey is doing the instrument and the algorithms. But it has a suite of experiments, and we basically wanted to take the UK DMC experiment, make it run in real time, provide more than just the little handful of data sets we got from space, and provide a real serious data set, and that's what they're doing. So the TechDemoSet, importantly, the TechDemoSet instrument is almost identical to the Cygnus instrument. So this is sort of providing flight heritage to the Cygnus instrument as well. Bad news is it only operates 2 days out of every 8 days, and to our frustration, we cannot control those 2 days. There were a couple of great big hurricanes this season, and we could not collect data from TechDemoSet just because that wasn't their turn. And they kept telling us, well, they can't play favorites, and we were trying to convince them, yes, please play favorites. Or please try to give us can we trade some days or something like that? Because we missed some big hurricanes. There were some big Cat 5 hurricanes this year, and we really wanted to get some data over hurricanes. That's the one thing UKDMC could not do. We never got high wind speeds on the UKDMC. So we want to see what the signals look like when the wind speeds are 30, 40 meters per second or higher. But they've released a large quantity of data. I just wanted to give my old colleagues a little bit of a plug. If you go to that website there, MIRBIS, I don't know what that stands for, but they're basically releasing the TechDemoSet data. And we have been going kind of nuts in the last couple of months processing this, some of the TechDemoSet data, myself and Andrew O'Brien at Ohio State and several others at the University of Michigan. But here's just an example of some of the public TechDemoSet data. This is downloaded for 1 day, and this is basically the UKDMC generated 25 measurements. In 1 day, TechDemoSet generated 630,000. So literally it's generating every second for 4 measurements for 2 days. And so this is the coverage you get. So we're getting just tons of data over the ocean, land, and ice. And this data is all publicly available. I show a little bit more of it later on in the presentation. But this is going to make things a lot, the validation of additional applications a lot easier. So now we've got the data to really determine what we're sensing on the surface and to what accuracy. So that's just what's up there. There's a lot of stuff in the works, and I'm not going to go through all of it, but Cygnus is my favorite because that's the one I'm on, so I'll talk a little bit about that too. But this is just basically a GNSSR overview. I'll go through this quickly because I think a lot of people know what's going on here. But from space, you get the forward reflection from the GPS satellites that are continually transmitting over the whole surface. When you get a COM-C, you basically get a very specular reflection, so you get a nice clear moon in that example there. It's not in the visible wavelength, but this is just demonstration. And then as the sea roughens, you get sort of a glistening zone, so the signal spread widens, the scattering widens across the surface. And then when you get the signal on the spacecraft, what it eventually looks like is these delay Doppler maps. And I'll try to, it's really hard to kind of explain how these delay Doppler maps look like they do. The big horseshoe shape is difficult to get your head around, but you can do it eventually. The key area we're interested in, though, is the hot spot right at the center. All the tails of the horseshoe are more or less the spreading of the signal and how it's mapping in delay and Doppler. But most of the information is in actually the fluctuations in the peak. Now, one thing I like to mention is just to see what we're measuring. If you go up to space, your surface resolution gets bigger. So if people are used to working with aircraft or ground-based platforms, you get a very small reflection footprint on the ground. You get very high resolution. When you go up in space, and in this case, we're working with GPS L1CA code, which is what Cygnus does, which is what TechDemoSet will do. Although TechDemoSet also has L2 they haven't released yet. But this is just a mapping of how the signal spreads on the surface. So what you have here is like the green ellipses, which you can barely see or kind of try to imagine, and then the parallel Doppler lines. So one chip on the surface from a satellite altitude will spread over about 20 kilometers square on the surface. So you are looking at a fairly big surface area for GPS L1 with its 300-meter chip. Of course, if you go down to, if you use L5 or another GPS signal, these green lines all shrink, but this is sort of the kind of the magnitude of the surface resolution we're looking at. We're looking at like 25 kilometer square resolution. That's the requirement for Cygnus. But that's with GPS CA code, that's what you're going to get. If you go up to L5, you improve by a factor of maybe 3. And just as a comparison, it is geometry dependent. So this is an example of a 10 degrees incident reflection. So basically your signal coming from 10 degrees off nadir. This is one from 40 degrees. And as you go out to 40 degrees, you can see the ellipse spread bigger. It's basically all geometry dependent, how the GPS code maps onto the surface and how the Doppler maps onto the surface. So any remote sensing that you got to do, you got to correct for this little effect here. So a lot of the return of the signal is completely based on geometry, not the surface. This is just a detail of a bigger version of the actual signal. And you can see on the y-axis is the delay. So the y-axis is the mapping of the green ellipses, and the x-axis is frequency, so x-axis is the Doppler. And what happens is the farther and farther you go out in Doppler and farther down in delay, so down is sort of increasing in delay. So the peak of that signal, I don't have a pointer, but just the peak of the top, the magnitude, the strongest point of that signal is right in the center. And then as it goes down, farther out in delay, which corresponds to down the page, you get the spreading in the sort of the wings due to the Doppler shift. Okay, now I wanted to just kind of jump right into, I had more slides on sort of the theory and how you model those reflections, because we do have some decent models to model the diffuse scattering, which I can do afterwards if we have time, but I wanted to kind of reserve some time for some nice little movies. Okay, good. Just quickly on this one, I'll do it on this one. So basically just a quick demonstration of ocean wind and waves. And this is 3 signals from the UK DMC. So here's your delay Doppler maps across the top. So this is delay, this is Doppler. This is for a case, when I did my PhD over at Surrey, we only had 25 or 30 collections, but I was clever enough to actually target those collections near NDBC buoys. So I did have some truth information as to what the sea state was when I collected data. So this is an example of a calm sea, more or less. So the wind speed was 2 meters per second. And you can see that the delay Doppler map, or the horseshoe, sort of tightens. And the way, for GPS people in the room, if you wanted to take it to the limit, and if you assume the surface was completely calm, no waves whatsoever, perfectly specular, this will start looking like just a regular GPS signal. So it'll give you 1,000 hertz in Doppler spread, and it'll give you 2 chips in delay spread. It reduces to basically a direct GPS signal. The spreading causes the wings of the horseshoe. This is the little bit higher winds, so 7 meters per second winds, and then 10 meters per second winds. And these are all based on NDBC buoys co-located with the reflection. On the bottom, what I did here is I basically sliced through the delay Doppler map this way. So I basically just took a slice at a given X point, a given Doppler at the center Doppler. And here you can see the peak and then the kind of the tail off here. So this peak and tail off correspond to this little strip of pixels there. Same thing here, same thing here. And the key thing here is it's inverted from a regular backscatter radar. In a forward scattering configuration, the rougher the sea is, the lower the peak is. So here for the calmer seas, you get a stronger peak, less spreading of the signal. As the wind speed increases, the surface roughens, the peak goes down, the spread increases. So you basically get lower peak power as the wind speed increases. Now, how this actually looks like when you put all the UK DMC data points together, and so these are the UK DMC data after I corrected it for antenna gain and path loss and a couple other non-ocean related parameters and the geometry. This is all the total locus of points from the 25 collections from UK DMC that I managed to get. And so this is basically the wind speed estimate from the UK DMC data and the wind speed estimate from the co-located buoys. And you get the typical diagonal, but it's obviously not enough points we want a lot more points than that. So this is basically just a preliminary demonstration that shows that for low wind speeds, so the highest wind speeds we got were about 16, 17 meters per second. For low wind speeds, and again, you got most of the wind speeds cluttering around 8 meters per second like they normally do. But the error on this plot is less than 2 meters per second RMS, which was important at the time because that was sort of the requirement we were claiming for Cygnus. That's generally the scatterometer requirement. If you want to be able to provide wind speeds to what's less than 2 meters per second RMS. And so we did that with the UK DMC. TechDemoSet, we're probably going to get a lot more data and really tie down some of the accuracies. But with 25 measurements, that's what we managed to pull off. For Cygnus, we're doing several things I wanted to mention to actually try to do this a little bit better. So first of all, we're going to have better calibration. The UK DMC instrument was not calibrated nearly at all. We just basically hacked this thing on at the last minute. It had the AGC running. There was all kinds of bit distribution sampling problems. So there's going to be a much better calibration on Cygnus. It's got a much better low noise amplifier. So the noise figure on the low noise amplifier is much better. And the statistically better estimation model function. So we're going to have a lot more data to basically do a better model inversion function for the wind speed. So we're expecting to get better results from Cygnus. And additionally, D, which I didn't put up there, we've got a higher gain antenna on Cygnus. So Cygnus is going to get a little bit better SNR because it's got about 3 dB more gain on the antenna. TechDemoSet, on the other hand, is going to give us a large, kind of a good pre-Cygnus launch set of validation data. if we can get them to calibrate it a little bit better. So currently the TechDemoSet is not using their calibration load, and they're running it with the automatic gain on, which I don't like. So they could do better than they're doing. Yes, John? About 12. Yeah. UK DMC was about 12. TechDemoSet was about 12. TechDemoSet is a smaller footprint because it's L1, L2. Cygnus is about 14 and a half. No, high wind speed, that's a good point. The high wind speeds is basically 10%. So the PI of Cygnus, I'll get into this a little bit, he's basically kind of copied the quick scat requirements and tried to bin them. So below 20 meters per second, 2 meters per second RMS. Above 20 meters per second, it's 10%. Now, that was something that we were a little bit worried about, and we're trying hard to validate. Because when you get up to 50, 60 meters per second, it gets, in trying to model what goes on in a hurricane, it gets a bit risky. But NASA actually admitted this was a risk because there was no validation. There was ground aircraft validation at the high wind speeds, but no spacecraft. So we're trying to do simulations to validate what the accuracy will be. But it is hard to hit that when you get way up high.
Scott, can you go back to the back slide?
Sure.
One more.
That one?
Yeah. Okay. So these slices actually, for already 10 meters per second, the peak actually exceeds noise level maybe by a factor of 3 or something. So what is that noise? Is it just a thermal noise mainly, or it's scattering?
What, this noise here? Or
yes. Because I can expect that with 30 or 40 meters, you will not be able to resolve anything on
you get more. This is a UK DMC signal, so we're going to get more signal. We're trying to figure out what the signal will be. If you go up, you're right. You get down. You have to average. You average non-coherently to reduce your speckle noise, and to reduce your thermal noise. So we average for for 1 second. So we're averaging 1,000 looks.
Yeah, but that was my question. What's dominating in that noise? Thermal noise or speckle noise?
This is UK DMC data. I think it's thermal noise.
Thermal noise. Yeah. So you expect to lower it with high.
Because the UK DMC noise figure was not good. The bit sampling was not good. There was an automatic gain control was on. There was a lot of things on the UK DMC experiment that were making the data unnecessarily noisy. We also had a lower gain. So Cygnus, we've got higher gain. We've got a much better low noise amplifier. So it's basically a custom designed low noise amplifier to give us a really good noise figure. We expect the thermal noise characteristics to be much better on Cygnus. But you're right, the sensitivity at high winds goes down. You're looking at, we're expecting, like from my personal experience, I think that the requirement to meet 2 meters per second below 20 meters per second, that's the easy part. I mean, because your sensitivity at low winds is good. When you go up to really high winds, you're basically if you can basically plot this, you look at you're on the downward slope of a curve, so your sensitivity really does go down, and when you're out at 30 meters per second, 40 meters per second, your error bars go up, your sensitivity goes down. So we're trying to, if I can just go forward a little bit to see how we're trying to convince we can do this, is what Cygnus is doing is we're running, because we don't have any data from space at that high wind speeds, we're running what we call a nature run simulation. So on the right here, we've got a simulated hurricane. This came from Dave Nolan at the University of Miami. And this thing spins up. I have a little movie of this thing spinning up and how the Cygnus coverage will kind of intersect it. And this is sort of the L2, preliminary L2 retrievals for the Cygnus data. And this takes into account the Cygnus noise characteristics, the gain, the orbits, everything. Also, Cygnus is a little bit lower than UK DMC. It's about 200 kilometers lower, so that's going to give us shorter paths. So we're doing everything to boost that gain up to give us more sensitivity at the high winds. But you can see here we get a lot of spread. You get very good results below 10 up to 20, and then you start to see the variance starts to go way up as your sensitivity and your errors go way up. And now here, how we're actually modeling up here is disgusting, because once you get into the details of a hurricane, hurricanes are not like standard winds, like normal winds, and all our models are used to modeling just normal, boring, constant winds, well-developed seas and all that. Hurricanes are the opposite. Hurricanes have some crazy wind wave dynamics going on, and so we're trying to quantify the errors we're going to get at these very high wind speeds. So yeah, if I can show the movie of that at the end, it'd be kind of interesting, because you can see actually how the Cygnus coverage will benefit. And the idea with Cygnus is they're going to try to get more. I'll talk about it a little bit later. But just moving on quickly to land applications, this is something I've been trying to kind of get some more momentum on. So So GPS and GNSS in general, pretty much everything, they're all in the L-band frequency, which for once is sort of the frequency we want for land, or at least a lower frequency, which is going to give us a little bit more sensitivity to soil moisture. It is very close to the SMAP frequencies. For oceans, the traditional scatterometers are a little bit higher in frequency, so the L-band's a bit low, so we're sensing longer waves, which we're trying to figure out the effect of that. But for land applications, we're sort of in the right frequency to begin with. But the catch is we got all this data over land now from TechDemoSet. We had some data from UK DMC, which I'll show. Cygnus is going to provide loads of data over land. It's not a land mission, but the instrument's going to be on over land, so it's going to be providing tons and tons of measurements over land. The biggest question is we don't really know how we can accurately sense soil moisture over land. There's not been a lot of work done on this. We know you're going to hit the same problems SMAP has and any land sensing satellite radar has. You're going to have to untangle the soil moisture from the topography, from the surface roughness, from the vegetation water content, from the cover, all of this stuff. And all that stuff is going to exist in a GPS reflection just like it exists in a regular radar or radiometer. But the idea is that because we're in L-band and because all these other existing instruments have to tackle the same problems, there is potential to kind of link the GNSS measurements up, which we're going to be higher frequency, and actually do soil moisture sensing, and then possibly actually go down to the root zone soil moisture. The key is that basically my idea for the GPS land reflections is that we're not really going to compete with SMAP. We're going to have to deal with the same problems with SMAP, but GPS can, in theory, go much more higher revisit times than SMAP can. So Cygnus is going to provide a lot of measurements. And I've been trying to get, and we just submitted a proposal with some SMAP people, and trying to get some GNSS research done to figure out how accurately we can sense soil moisture, how that will benefit SMAP and the SMAP models, and how these repeated measurements, even if they're less accurate than what SMAP can produce, just the pure abundance of them could help tying down the SMAP passes and stuff like that. But we need to give an answer, because if you ask me the question, what is the accuracy GNSSR can sense soil moisture at, I don't know. You need to really do initially the first preliminary studies to figure out what that accuracy is and how it would help existing models for root zone soil moisture, for all the dry down profiling and all that good stuff. We need to really do some preliminary studies first, validate them with Cygnus or TechDemoSet, and then see how if we can pull these into some sort of operational context next to SMAP. Okay, here's my favorite reflection. This is from the UK DMC. I'll have another reflection from TechDemoSet. But this just shows the sensitivity of the things on the surface. So what we have is the first 2 seconds. This is the data collection near Omaha, Nebraska. And so the first 2 seconds of data, you get nothing much happens. But the only thing we really detected here was you got that big spike at second 2, which is basically the signal crossing the Missouri River. So you get a nice coherent reflection off land. It hits the river, which was in the winter, so we don't know really what was going on in the river. It was snow-covered or what. You get this huge coherent reflection off the river, and then basically straight back down again. And then interestingly, it kind of a few seconds later, you get additional river crossings off the Lou River that actually kind of winds around. You get 2 crossings, one at second 12, one at second 16, and also a general increase in the power along the kind of when it is traversing the river. Now this is more just kind of a tantalizing thing. I was like, what's going on down there? We don't really know. I've looked at USGS maps. I've looked at everything, weather underground. I knew it snowed that day. There was basically all kinds of things going on. There's all kinds of things I can't explain in the plot, like this little drop here. I have no idea what that is. I think it could be the automatic gain control on the receiver, just automatically jumping the power. But all this kind of sensitivity here, what that's actually sensing, this sort of general increase here, these 2 river spikes are sort of our references, and this big river spike is a reference. So it is sensitive. It is responding to the surface. But this is why we need to really do a proper study, an OSDI of some sort, to actually figure out what we're sensing and how accurate. Yep? This is the signal peak power. So this is the peak of the DDM. So you can look at other characteristics of spread, but this is basically just how high your peak is. So when you go over the river, you get a very sharp, coherent reflection. Bang, the peak spikes way up. And then as here, we don't know what's going on here, whether there's some sort of general increase or flattening of the surface that could cause more return of the signal power. And then these are definitely river crossings as well. So that's the Lou River kind of comes in and does a loop, and you hit it twice, bang, bang. Okay, just the last thing, I did show some TechDemoSet data we did. And by the way, this actually did go into a proposal. So we actually did submit a proposal to try to say we want to try to develop a soil moisture sensing algorithm. We want to try to use TechDemoSet to help us out. But this is a TechDemoSet pass of Australia. And so you do get 3 signals from TechDemoSet. The signals from land are fairly coherent. You get less of a horseshoe off over land, and it looks a little bit more like a direct signal. So here you have the tail here. But these other 2, especially this last one here, it's fairly tight. And so it starts to really, you don't get a lot of spreading in the signal. And the one of them was over savanna, the other one was over shrubland, and then this one was sort of mixed. And this is basically the peak of the signal power here. So we don't really know what to make of this yet, but we're going to try to actually use, if we get selected, which is not by any means a sure thing, use TechDemoSet data, use the models, and try to figure out if we can come up with an algorithm to distinguish between different land types, try to estimate soil moisture, using both TechDemoSet data and Cygnus data when it's launched. Okay, so I think basically just a summary as to what I said. I'll go quickly through this, but it's basically it's the correct, more or less the correct frequency. We might be able to provide higher frequency measurements, which would be good for helping the models, even if the measurements prove to be less accurate. You still have all the same problems with GPS as you're going to have with any kind of radar. You're going to have to untangle all the nuisance parameters, topography, roughness. And just as the proposal's already submitted, but we basically just took the same approach SMAP did. We're going to go with a SMAP-type data cube. So you're basically going to try to just do a great big giant empirical function with all the different main surface cover, topography, and then soil moisture. So we're kind of taking the same approach that SMAP would and using some of the SMAP tools that have been developed already. So additional studies, we definitely did need additional studies. We got one in. I'm sure other people are doing this as well. I'm sure, because everybody knows in order to sense soil moisture, you need more study. So I'm submitting this. I submitted this with Ohio State and Goddard, and I'm sure JPL's got their own. But somebody eventually is going to get a study and try to figure out what soil moisture can be sensed and to what accuracy. Okay. Almost lastly, I'll do ice sensing kind of quick. Ice sensing has got a lot of TechDemoSet's better for ice sensing. But basically, I wanted to just kind of do we did get a couple good UKDMC reflections over ice, and ice reflections were really, really sharp. So basically, we got very strong reflections off ice. Strangely, the TechDemoSet reflections are very strong, but they're not as strong as we saw in the UKDMC. We're not sure why. It's probably because they have more of them. We had only 2 or 3 data set points on a UKDMC, whereas TechDemoSet has got hundreds of thousands by now. So basically, we get, again, with ice, it's more difficult in a lot of ways than ocean, where oceans kind of lends itself to some different kinds of modeling. Ice is, again, just a very complicated thing. Once you get into the details of ice roughness, the structure of the ice, all the penetration into the ice, the reflection off the ice surface, and then the water underneath, the modeling problems really become much more complicated. So you're sort of in the same boat as with land sensing. You really got to do an OSSI study. You got to look at the data that's up there. You got to come up with a good ice model that actually can figure out what you actually are sensing on the ice. One of the things that I do like, though, is high potential. I think high resolution ice edge mapping, I think, would be a very good application, just based on the fact of how quickly those signals jump when they go from land to water. And TechDemoSet has seen this as well. If I got a time, I'll show a movie of TechDemoSet at the end that's on YouTube. It's a public domain movie where you can really see the TechDemoSet DDMs go from horseshoe, bang, to right to almost a coherent reflection right when they hit the ice edge over the Antarctic. So I think that's possibly one application. Ice concentration is something that could be kind of interesting. I did try to do a look at this with the UKDMC data. Ice thickness and ice altimetry are kind of the long shots, but I put them down there anyways. Yeah? I don't know. It could be, if you get some phase information in there, this is a big debate. We got a UKDMC reflection which had coherent phase in it. And we're trying to unwrap that phase. And if we can get that phase out, we might have you might get some dual reflection. But I'll admit, ice thickness is a real long shot. I don't really have a whole lot of hope for ice thickness. The same thing with ice altimetry. You could probably get accuracy, but there's not a lot of coherent phase in the signal. And even if the coherent phase that is there, we're finding right now, it's almost impossible to unwrap the phase and get a phase range. I think that the better ones are ice concentration, possibly ice roughness, and then the ice edge mapping. You might be able to see the transition as well. Okay, this is just a demonstration, one of the most interesting. This isn't, we have basically two really interesting reflections. One of them is with the coherent phase, but it's a really boring ice condition. It's basically just really smooth ice. This is basically a UK DMC reflection where north is up the page. We got a reflection that started over high concentration ice and then transitioned to lower concentration ice. This is a chart from the National Ice Center. And I was interested to see how the UK DMC data power fluctuated over that transition as compared to the map. So try to keep that in your mind as I talk about this, because this one's kind of hard to get your head around. What we got is, in the UK DMC data, you got this sort of delay waveforms here. So you got these delay waveforms with high magnitude. In this case, I wasn't averaging over a second. I was averaging for only 100 milliseconds. So you get more noise in there. I think we're getting some speckle noise in there as well, because I wanted to keep the resolution high. So you get a lot of fluctuation in the magnitude, but the magnitude generally is much higher. And then as soon as you get that transition there between the high concentration ice and the lower concentration ice, the magnitude goes down and the reflection becomes much more diffuse. So you get a lot less fluctuation in the signal, a lot less, and then you get more of a lower typical, much more like an ocean scattered signal. You get very kind of more spreading in the delay and the Doppler waveforms. And this is how it looked like compared to some other instruments. So here again, you got to kind of twist your head around. This line here is the start of the GPS data collection. There's the end of it. You can see these data collections on the UK DMC were very short. I would have loved to have more data and the data continually off and to see what we could have done here in the transition zone. But this is the National Ice Center data. So that's where they said it broke off. This line here is AMSURE. So that's basically AMSURE concentration. So AMSURE said it broke up at about the same point, and then but the AMSURE is kind of predicting it was actually more of a gradual breakup. The GPS data has quite a distinct drop off. So in a sense, the GPS is predicting kind of a little bit a different profile on the breakup than AMSURE was predicting. But everything is sort of in agreement that the breakup started happening at the same point. So what this is just one reflection. This is, again, kind of like the starting point of trying to do this, validate this with a much larger data set and with some better ground truth on ice. Okay, so this is in very little space-based validation. People, hopefully, are proposing projects to actually do more ice validation. TechDemoSet's got a huge data set. Cygnus will not see any ice. Well, it might over the mountains or over the Himalayas or something like that. It will see frozen ground in southern Colorado, which might be interesting, but the Cygnus orbit is only up to about 38 degrees latitude. So TechDemoSet is going to produce a lot of ice data. Cygnus will not, because Cygnus, as I'll describe later, was basically designed to target the Caribbean and the lower equatorial latitudes. Okay, so there could be some interesting applications. I mean, like I said, there's some long shots, but I think the higher resolution, the transition from ice to ocean could be interesting. If we get a lot of these, the huge data set, and if we get a ton of measurements, there could be very good maps of ice resolution, which could be even quicker than the existing ice instruments. The strong coherent component could be interesting in doing that, and you could also get there are some long shots you can do this. I always put those up there, but we'll see where those go. And ice concentration might be an interesting one to do, if the resolution can handle it. Again, remember the resolution is only about 25 kilometers for L1, maybe about 10 kilometers for L5. Okay. Now off to Cygnus. Just a generally kind of overview as to what Cygnus is Cygnus selected a few years back. The University of Michigan is PIing it. Professor Chris Ruff is the PI. It's basically a team between University of Michigan, Southwest Research, who's doing the satellites, building the satellites down in San Antonio. Surrey Satellite Technology, both in the UK and in the US, is doing the instrument. And this is, as I mentioned, this is pretty much the same instrument flying on TechDemoSet. The goal is basically the very clever niche that this thing is going to address is that there's been very little improvement in predicting when a tropical cyclone is going to intensify or not. So they can better predict where it's going to go and a lot of things by using modeling, et cetera, et cetera. But when it's going to intensify has always been a problem. And what Cygnus will do, in theory, is it's going to provide rapid measurements of wind speeds in and near the eye wall. So that's going to improve hurricane modeling and hopefully improve prediction of when the hurricane is going to intensify. One of the things, and this is one of the reasons I was coming here, is because in addition to that, it's not all wind speeds. And when a hurricane intensifies depends on a lot of things. Wind speed is only one of them. And so the other things they need there, I think, is in order to really get a good handle on when a hurricane is going to intensify, you need information on the atmosphere, the ocean temp, the currents, tons of stuff. So Cygnus is only providing one piece of this puzzle with the goal that they want to basically better understand when a hurricane is going to intensify and when it's not going to intensify, because historically we're very bad at predicting that. So the Cygnus design was an 8-satellite constellation all in the same plane that will provide repeats of about 5 to 6 hours over the hurricane. Now, because people who have done orbit analysis, coverage analysis, know that if you put 8 satellites in a single plane, you're going to get this sort of strange sync between the ground and the plane, and so you get these measurements all in a little burst, and then you get a big gap as the Earth rotates under you. Then you get measurements in an additional burst, which is why I'm sort of thinking ahead to the future, and if we're looking at low-cost missions, you want to do bigger constellations in more than one orbit plane, and then you get ridiculously good coverage, like on the order of hours. So this is what the satellite looks like, just in case there's any engineers and techies in the audience. This is the instrument right there. It's about this big. It draws about 10 watts, tracks 4 channels. This, initially, we were planning on doing Cygnus with a 3U CubeSat, but it turns out we couldn't. So the middle here is more or less a 3U CubeSat. So this isn't that big. The whole satellite you could pretty much hold in your arms if you were strong enough. But that's about just slightly bigger than a 3U CubeSat. They put some avionics on the outside. The reason it looks like it does is to basically accommodate the antennas. The antennas are basically double the size of the UK DMC antennas to give us about 14.5 dB. We needed these wings to basically mount the antennas on. Inside the wings is pretty much air, so there's not much in there. There's basically, see a picture of the LNAs. There's an LNA, I think. So the LNAs are fancy little LNAs for each antenna. There's 2 downward-looking antennas. They're cocked off to the side so we can look in the cross track. So we actually have a beam oriented in the cross track, so the measurements are kind of scooped up with the motion of the satellite forward. And you have a nadir antenna, which is just a GPS L1 simple navigation antenna. Surrey satellite in the UK. Yeah. This is what one orbit looks like for Cygnus, and you can see this is about 35 degrees. And the way they targeted the orbit was they did some historical analysis of where the hurricane tracks were, and then most of the hurricane tracks are between plus and minus 35 degrees latitude. Of course, you do get a lot of hurricanes that kind of curve up in through here and eventually are going to curve out of our window, like Sandy, for example, and things like that. And you do get a lot of high wind speeds up here, but the whole major design was to basically when they're actually down here and causing real trouble and over here is you want to have the measurements on them then. So the coverage was optimized in this window, and this is what it looks like for one orbit. This is what it looks like for a day. And I like to show this just because gets people used to what the GPS measurements look like. They're weird. They're probably a little bit like, I guess, occultations are weird too, but you don't get an image. You don't get sort of a traditional SAR kind of image and these tracks, and you get these sort of synchronizations between the receiving satellite and the GPS constellation, which is in MEO. So it's up there at 20,000 kilometers altitude, and your satellite's down at 500, 600 kilometers altitude, and you get these sort of strange pseudo-random tracks. So you have to look at coverage as a probability, as a random process. And so you get these sort of random tracks based on your antenna, based on your orbit, based on the GPS orbits. And over a day, it all fills in. So effectively, it's over a day you get complete coverage. But if you look at the details, you can say here, if you look at this whole map, there's places that have gotten hit 3, 4, 5 times. And there's places like you can see little white patches where they haven't got any measurements at all. So it's a very random sort of measurement coverage. And you get by basically putting up more satellites, tracking more measurements, and it's basically just a logic of hit it with everything you got. You launch these satellites are much cheaper than big satellites, so put a lot of them up there, get as many measurements as you can, and eventually you get that as quick as possible. And then once you get that, that's sort of your overall coverage. Now, what I wanted to do, which I got to get into CocoSet. So I basically took the CocoNet coverage and off one of your flyers, I stole it. And so this is basically your number. So that's a nice little GPS network. So we have Cygnus measuring sort of the same area. So you're looking at here, Cygnus is sort of concentrating its coverage right over there, pretty much mostly, but this is where it's going to be doing a lot of hurricane tracking. And there's your CocoNet Caribbean network. So what I did was I did a typical coverage simulation as to what Cygnus coverage would look like over this region here. And what I got is this. And so this is a 24-hour track coverage, and you can see it's hard to see because but it's the same region. So it's between about 6 and 25 north and 96 and 64. So this is the same region. Here you get the black traces are all the downward passes. So Cygnus constellation comes over 8 satellites, bang, 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 about 20 minutes apart. These are the kind of a flurry of passes you get, and then you wait about 6 hours, and then you get the green ones. And so what you're going to get over a period of a day, you're going to get good coverage from Cygnus over the whole region that corresponds to CocoNet. So there's going to be a lot of co-located data. I'm assuming CocoNet's taking data continually. These are going to be, Cygnus data is going to come over every 6 or 12 hours or so, and you're going to have surface measurements and measurements from other GPS receivers and possibly a lot of occultations in there as well. So there's lots of things. You get measurements that are going to start to come together once Cygnus launches. And I haven't even included TechDemoSet, so TechDemoSet's coming over this area as well. This is revisit time, so this is kind of hard to determine. I wanted to show this just because for over a day, you can see like sometimes these points here in red only get hit once per day, so you're only going to get one measurement in these boxes per day. Other, just depending on how everything lines up in the antennas and the GPS orbits and your orbits, you get definitely revisit time. So you got these points in here that are basically around here getting hit 4 or 5 times a day. And that's where they get the, on average, 5-6 hour revisit time. So if you look at everything statistically, you got points that are going to give you good 4 or 5-6 hour revisit times for every point. And then you got these other sort of points out here where you're only going to get 1 hit a day. But just on average, everything piles up. And you're going to get good coverage over both regions. Okay, the future. Now, I wanted to kind of go, one of the things I've kind of locked onto is basically Cygnus is great, but when you start doing coverage analysis and you look at how small these satellites need to be, you don't need to do, if you don't do altimetry, so if you don't need a great big antenna and a lot of processing on board, and you're just looking at, let's say you don't want to do really high ocean wind speed, so maybe you can reduce the antenna size a little bit, you could do this sort of a GNSS reflection mission on something like a CubeSat or something close to a CubeSat, maybe a 3U, maybe a 6U, and still get good results at, say, low wind speeds, possibly over land. Now, when you start getting the satellite that small, so even smaller than Cygnus, so the Cygnus satellites, I don't know, 5, 10 million each, who knows, if you bring those things down to CubeSat level and you're looking at 500,000 to a satellite, then you can start doing huge constellations. And then the problems start becoming, how do you do orbit maintenance? How do you get them into the right planes? But just to kind of get people interested, I like to do these simulations of future constellations where you take additional satellites. So instead of taking Cygnus 8 satellites in one plane, I'm going to triple it. I'm going to do 24 satellites in 3 planes. And when you do that, you get stuff like this, which is just ridiculous. So now if you look at coverage like this, any Earth scientist in the world is going to see that and be like, well, whatever your measurement accuracy is, that coverage is just so ridiculous. I can't even. There's definitely things you can do with that. If you're seeing every point on the globe in every hour, even if the land measurements aren't as good as SMAP, but if you see measurements that fast, if you start seeing things up at the, if you even look at, you can even optimize this a little more. So this is basically with all the 24 satellites in polar orbit. If you start being smarter about this and start staggering the inclinations, so the revisit times up at the pole are about 20 minutes. Every point up at these high latitudes. And then on the equator, you're looking at, say, maybe 2 hours. But if you actually kind of design the constellation, have some control over what planes you can put them in, you could actually skew this towards the equator and get more or less, say, maybe an hour and a half revisit time everywhere, all the time. And this is kind of what with the number of satellites, with the satellites becoming cheaper, and you could do this all for the cost of Cygnus or maybe a little bit less, but we're still talking way, way less than something like that, than the big missions. And if you can get something like up this in the future, and this is sort of just my little soapbox now, I think this is where it should go and where it could easily go. And if you get constellations like this, doing reflections and maybe even doing occultations as well, the coverage is going to become ridiculous. So Cosmic now is, what, 8 satellites, or Cosmic 2 is more than that? 12. So the satellites are getting up higher and higher. So the Cosmic 2 coverage probably looks similar to that. But this is just sort of the exaggeration of it. So the satellites get smaller, the constellations get bigger, the coverage is going to start to fill in everywhere. And if you can get occultation coverage and if you can get reflection coverage, you're basically seeing from the surface up through the atmosphere almost at a constant rate. Because this is the problem I had with the synchronizing occultations and reflections. People say, oh, they're the same as GPS or whatever. Don't they work? They work together well. Yeah, the problem is occultations are looking at the limb. Reflections are looking down. So they're not looking at the same spot at any given point. So what you need is an occultation within an hour of a reflection. You're going to get it from different satellites. So you're going to get one satellite's going to take the occultation over where the reflection happens from another, and you only really get that to a point where it works when the constellations are big enough and you get enough measurements just to cover everything. Because measurements on a single satellite are not looking at the same thing, and so it's really hard to make a case that would work together. You're going to have to work with an occultation measurement on one satellite and a reflection measurement on another satellite, and the only time you're going to get the spatial temporal coincidence that's useful is if you get enough satellites and enough measurements up there. Okay. Now this is kind of the last slide, I think. And then I'll show a few movies if people are interested. But I wanted to kind of just throw out some possible areas of new research. So one of the things I'm kind of trying to look for is Cygnus is doing the ocean winds and the waves. You've got Cosmic doing atmosphere. You've got CocoNet looking at measurements on the surface, also doing sort of all kinds of occultation on the surface. It's got to be useful. I've kind of latched onto this idea and won't let it go because I'm not really an atmospheric modeler. My expertise is more in the instrument, in the raw measurement. So doing the raw measurement, what you do with that, and how you actually combine these raw measurements, I need people who can kind of have the expertise to put these all together. But I've sort of grasped onto the idea, and I'm not going to let it go until somebody convinces me it can't happen, that if you have a measurement of the surface from Cygnus, of the wind and waves, and you have some other measurements from either CocoNet or some sort of occultation measurement from Cosmic, you basically can put together a model from the surface right up through the atmosphere. And you might be able to get these really nice profiles right through the atmosphere, right down to the surface, and actually measure the surface, the wind and waves on the surface, right up through the atmosphere, or as to how far down an occultation can go, or how far what CocoNet can measure on the surface. So looking at sort of how CocoNet, Cosmic, TechDemoSet, Cygnus can all work together at some point, I think makes for some really interesting projects, because I think these measurements by themselves are sort of interesting. They have their own little applications. But I'm just sort of convinced there's got to be some synergy with these things. Once you start getting enough measurements up there, and the measurements are looking at very close to the same spot at very close to the same time, and that's the big question is how close is good enough and how close temporally is good enough? Can we do, if you get a Cygnus measurement and then you get a Cosmic measurement 3 hours later, is that still good enough? And what if they're not co-located exactly? What if they're off by a couple hundred kilometers? Is that still useful? I'm still thinking it's yes, but these constellations are getting so complicated and the measurements are getting so diverse, they really need to, I think looking into that is a really good thing to do in the long run, especially as these GNSS constellations are going up, and then more Cosmic constellations are going up. And CocoNet is already there, and hopefully it'll continue to work. And so you'll have all these measurements, you have all this data at some point, and then how to put that data together, I think could be a really interesting. Okay, I think that's all I had. I wanted to get to show, basically I had perfect timing. I wanted to show a few movies. Okay, let me think of make this democratic. Okay, the first one is I can basically show you the hurricane coverage movie, which is kind of nice. This is basically, now what this is a simulation done by Dave Nolan at my University of Miami. Ohio State actually did the end-to-end simulator. What you're going to see here is a hurricane develops. So this is basically a big nature-run hurricane simulation. It basically kicks up. Now what that crazy stuff going across the screen is Cygnus measurements. So what they've done is they've taken every Cygnus satellite, they've given a measurement from each of those satellites a symbol. So that's why the symbols are all different. But this kind of gives you the pattern. So you can see, this is latitude here, so it's still pretty low. As it goes up higher, you can see it flatten out. But as the hurricane develops, you'll see you get these gaps. You can get these gaps in an order, and then as the Earth plane rotates under, you see you just get tons of measurements coming over from all 8 satellites in the constellation just cruising over and hitting it. Now, once it gets a little bit more interesting once it actually develops into a real hurricane. the model box is huge. It's basically plus minus 35 degrees. Okay, so we only lose it when it goes above 38 degrees. So the Cygnus orbit is 35 degrees, but you get coverage up to about 38 just because the GPS satellites are north of 38 will give you a reflection point north of 35. So you get visibility up to about 38 degrees. So here the thing starts to develop into an actual hurricane. And so this is all the measurements you're going to get. And so the measurements they're really interested in are those little tracks that kind of go right through the eye wall and kind of give us measurements right in the eye wall as it's intensifying. And there is a point in this simulation that this is basically a simulated hurricane. I don't know the exact details of how they do it. They do anchor it somehow at the historical hurricanes, but the guys down at Miami and at NOAA and the Hurricane Center know how to model hurricanes. So this is what we used to sort of validate our wind sensing algorithm. Right. So the most interesting thing here is you do get these kind of instances where you have this great coverage, the satellite's just flying over, you're getting measurements all across the hurricane. Then you got these sort of breaks where the satellite's on the other side of the Earth and the Earth is rotating around. Now if you take and you move this into like a 3 orbit planes or 2 orbit planes, then you'd basically just give one after the other. You'd basically one would leave, you'd wait 2 or 3 hours, and then you get a bunch of another group of satellites would come by and hit it. So this was with one plane. Now, interesting, I didn't talk too much about Cygnus, but Cygnus doesn't have any propulsion. So it's basically going to have, it's using an orbital differential drag technique to basically make sure the satellites stay separated and don't clump up, because if the satellites all clump up, they're making the same measurement, which is not good. So you want to keep the satellites spaced out in their orbit plane. So it would also be kind of nice just to have a little bit of orbit propulsion on any kind of satellite we put up. On a CubeSat, that might be tough, but for basically keeping the satellites nice and separated, and if we actually do want to come up with a cheap way to get them into different orbit planes, it's nice to have a little bit of propulsion. Okay, done. They're all launching. One. Yeah, they're going to launch in one big thing. So basically, there's a vehicle being designed by Sierra Nevada, actually in Louisville, and they're all launched. I had a movie of that too, the deployment sequence, but you might be tired of movies at that point. Okay, the next one is. Let me just do the Cygnus fancy video. Can't believe they actually, I don't want to hear the music. Okay, this is something, I mean, Southwest has got a nice overhead budget, so they can do nice videos to impress NASA. But this is basically the Cygnus observatories are sort of right there. And this is the antenna patterns projected onto the surface. So they're basically the left and the right projects in the cross track, and the satellites move along, and these are the GPS reflections. And as soon as the reflection moves into the antenna pattern, this is where our measurements are, like right here and here. So these are the measurement tracks. These are basically the different GPS. Every GPS satellite has got its own little measurement track. The instrument on is basically been coordinated with some sort of rehearsed dialogue, which I don't know. But the instrument itself can track 4 specular points at one time, so that's the max it can do. And you usually get that. So our antenna patterns are wide enough that you usually get 4 reflections at once. TechDemoSet, on the other hand, has got only 1 antenna, and it's a narrower beam. So if you look at TechDemoSet data, they often don't get 4. They usually get 1, maybe 2 reflections at a time. But we've got the antenna coverage to actually give us all 4 most of the time. And the measurements go out there. We basically have sort of a little bit based on the sensitivity. So once the signal gets too weak, so once the gain of the antenna is too low and our predicted SNR is too low, we don't even bother making a measurement. So, for Cygnus we can't because the instrument's fixed. It's basically on, so it's L1, L1. Yeah, but we are looking at other GNSS. For the big one I like is L5. Or the Galileo E1 because you get better coverage. I mean, eventually at some point when your instrument can track more signals, you're going to need more satellites. So if you can do GPS L1, Galileo E1, that gives you a lot of satellites and give you good coverage. But L5 and E5 potentially give you higher resolution. And So that's going to be, it gives you, the algorithm is different. Your thing shrinks on the surface, so your SNR is going to be affected, but you're going to get higher resolution with L5. You can possibly do altimetry, you can do high resolution scatterometry. So we're definitely looking into that. But for Cygnus, is going to be L1 only. TechDemoSet is L1, L2, but they haven't published any L2. The last movie I'll show you is the TechDemoSet movie, which is on YouTube. Okay, see, so TechDemoSet usually only gets 1, 2, or 3 DDMs, but here's the TechDemoSet. There's its reflection points. What it did here is it basically collected some raw data, like the UK DMC, and why we're not getting DDMs now is because it's downloading the raw data off the instrument. And then once it's done with that, you'll start getting DDMs up here again. All right. And just because limited to the antenna, the antenna footprint's smaller. They don't usually get 4 reflections. They usually get 1 good one and then maybe a couple stragglers. But it depends on the geometry and just the smaller beam on the antenna at TechDemoSet and lower gain. So interesting, as it comes up to ice, you'll see actually once it hits the ice edge, like that one right there, the signals go from the horseshoe and they quickly just zoom right into the tighter, smaller ice reflections. So you really do see quite well the transition between the ice and the water. And this is on YouTube, by the way, if anybody else wants to go dig it up. They basically published this. And the one thing that I hope I did kind of somehow subconsciously convince Surrey to do, when I was there, I was always raising a ruckus that they should have released more of the UK DMC data publicly. It would have helped get more people to look at it, and I was never able to do that, and I even ruffled a few feathers by releasing 3 data sets. But I got permission to do that. I didn't just kind of go rogue and release them. I actually got permission to release 3 only, but that was always a struggle. And so with TechDemoSet, they've taken a little bit of a different approach. They are releasing the data. So the data, literally millions of measurements are going on that MIRBIS website. So then it just comes up over here. So it's doing this continually. TechDemoSet is on for 2 days out of every 8 from when they're told they can be on, not when we'd like them to be on. But and all that data, as far as I know, is going on the website, the MIRBIS website. Okay, that's all I have. That's all the only videos I have. Thank you very much, and I hope you found it interesting. Thank you. Yeah.
Made some comments about trying to coordinate or develop some plans with COCONET.
Right.
So COCONET has a number of different observations. It has ground-based meteorological sensors that have wind speeds locally, but the primary component of COCONET is a GPS receiver that's an antenna system that's designed for positioning. Right. So it's not optimized for GPS IR.
Right. Do the COCONET GPS receivers, do they track occultations, or do they track the signal as it goes through the atmosphere and try to make any sort of ground-based?
It's not an occultation, it's a delay. Yeah. So I'll let John address that. So as a data product, so I was more interested in figuring out what you saw was an important contribution from COCONET because COCONET's build-out phase is coming to a close, and we're going to be seeking additional funding to keep it operational.
Right. Any kind of like in situ, I mean, these are all on land, I assume. So basically, but any kind of in situ meteorological data. If you got wind speeds on land, I mean, look at you're basically measuring over the whole sort of ring in the Caribbean. So if we have wind speed data even there, even if it's on shore, to couple that in with our validation campaign, with while we're looping that into buoys and different instruments and all this and that. One of the reasons I wanted to come here is I wanted to ask what COCONET produced. If these receivers actually did attempt to do some sort of, or more than just sort of earthquake sensors and sort of the high precision. John, do they do any atmospheric?
Atmospheric, yeah, COCONET derives atmospheric delay from every site.
Okay.
And so that is one component. Things that are possible are also looking at sort of boundary layer strength and things like delays. I'll ask you a couple of questions in private about.
Okay. Because one of the things is was not completely aware as to what the measurements being provided were. I knew that you're doing all the earthquake stuff and all the high precision
So one area where I catch a little bit of grief from my UNAPCO partners is that I like to have our sites on the smallest island as possible. We have maybe 4 or 5 sites that are very close to ocean surface measurements. They're the hardest for UNAPCO to maintain, but I think that they have significant value for things like this.
That's one of the things, is because I know you guys are doing, you and Christine Larson and other people are doing these ground-based receivers that are actually looking at the coherent reflections close to the receiver. So now, are you actually getting ocean reflections from some of these?
Maybe half a dozen CocoNet sites are being used for tide gauges.
Okay.
So there is a spec. So there are some they are very close to being land surf.
Right.
You know, you have tides and you have waves, and they're very close to the land. But yeah, those are about 6 of them are being used.
Because one of the reasons, I mean, if you look at the footprint, if you got a 25-kilometer footprint, it gets hard. I mean, in the ocean, you got a kind of good pure ocean measurement. But once you start getting land in that footprint, the Cygnus measurements could degrade in sort of unknown ways. So having good in situ truth on what sort of the near coastal conditions are might be able to bring the Cygnus measurements closer to the coast, which would be very useful. Okay.
Not on every one, but.
Right.
Regarding the soil moisture studies, do you think you'll ever work up to get some kind of land surface models, or is that really just something too far off?
What we're doing, and this is like, I don't know if it's going to happen or not, but what we actually proposed, so we actually, the proposal we did was with Joel Johnson and Ralph Reichel, and those guys are both on the SMAP team, and Ralph Reichel has got a huge database of topography that they're using to validate SMAP. So he's got topography and simulations for the small scale roughness, the seasonal changes. That's what we were using. I forget what they call it, Gleason or something like that. But we do need, for another proposal I did, I basically was using just data from one of the DACs at JPL. It was basically just looking at height data. So we were just taking height maps from JPL, global height maps, and converting them into mean square slopes and trying to do something there. But definitely for any kind of land sensing, we need models of the surface topography, the small scale roughness, the cover, everything, because that's all got to be taken account if we want to get to see what the soil moisture is. So I'm kind of agnostic. I mean, if I'll use the SMAP, if I get this project with the SMAP guys, I'll use what they have. If I don't, I'll use something else that's out there.
So, but he will not be deriving surface topography with Cygnus data. I mean, the footprint there is 20 kilometers, square kilometers.
Yeah, it's going to be a lot.
Her topography is 30 meters.
Yeah, it's doing a big averager. So
he's using an external data product as his surface.
Yeah, I'm looking more at the topography as a nuisance parameter, not as a measurement. I'm trying to get rid of it.
Actually, I was thinking more on the lines that when you have like global models of soil moisture at some point in the future.
I hope so, but it depends really on what we can do. Yeah, I mean, but John's right. The resolution is going to be, you're not going to get a lot. You're looking at a 25-kilometer average, or even for L5, you're looking at a 10-kilometer average of everything on the surface. So could be. I mean, yeah, that's where I don't know what's useful or not. I'm not really, it's just a what's useful or what's not. So we might be able to there might be some hidden one man's nuisance parameters and other one's measurement. So depending on what comes out, could be interesting. Yep.
Does this instrument have any sensitivity over the ocean to wind direction as well?
That's the best question we always get. The answer is Cygnus is not on the hook to do wind direction. Wind direction's tough. There's no real directional signature because according to the models we have, there's no directional signature at specular because of it's a diffuse scattering model, and we've looked at this. There is some directional sensitivity in the tails. But then so you look at the shape of the DDM. If you get the whole DDM and you get enough SNR on the tails, there is some wind directional dependence there. My idea for this is basically it could be really, really hard to get wind direction information out of Cygnus, but we're going to try. On future missions, what I'd like to do is, and this I've been reading up a little bit on this, is some radars use different polarizations to do wind direction. So if we can get a next mission that has like maybe two polarizations, even if the right-hand signal is going to be way weaker, if we can somehow design an antenna to get us a right-hand and a left-hand polarization, we might then start seeing the two-hump directional characteristic of the wind and do wind direction. But the quick answer is no, Cygnus can't do wind direction yet. There are several ways we're looking into doing it by either using the tails or possibly just, maybe the models are a bit wrong. Maybe there is some directional dependence on that peak. If you basically look at the rotation and the wind and the direction of the wave. So, and you're going to get dual reflections. So the way QuickScat normally does that is they take a look at one angle and then the satellite moves forward and they scan and they take a look at another angle and you get two looks at the same point from different angles, from different azimuth angles, and they use that to do wind direction. Cygnus might be able to do that, but it's not going to do it in one go. It's going to have to do it between two satellites. So one satellite's going to have to take a look at a point. Another satellite's going to have to come by later, but not too much later, look at the same point from a different angle, and then we might be able to get direction. But our current plan is to basically use some external information to derive wind direction. So we're just going to do wind speed only, bring in something else that we know can do wind direction better than we can, and then on the side try to come up with some kind of algorithm that can do wind direction with GNSS. Because people ask that all the time. Can it do direction? Not yet. That's a big kind of weakness we're trying to solve. If it could do wind direction, that'd be great.
Is it phase and pseudo range on TechDemoSet?
Sorry?
Is it phase and pseudo range on TechDemoSet?
This is all, the DDMs there? It's all non-coherently averaged, so there's no phase, there's no coherent phase. So you get that, when you're averaging 1,000 looks, it's all a diffuse scatter, so you lose all original phase coherency, except when the surface is really, really calm.
I think we'll go ahead and stop there, and let's thank the speaker one more time.